Hi everyone, this is video number 6C, and in this video you are going to learn how to name organic compounds and organize them according to their classes. So here are a bunch of questions for you to read. Please try to answer these questions. Identify whether the following statements are true or false. Take a moment, pause the video. If you don't know how to answer these questions, that's okay. You should be able to know how to do them, how to answer them at the end of the video. So let's get started. Again, our topic for today is to name organic compounds. So let's keep in mind that when it comes to organic chemistry, you always want to look at tables P, Q, and R. Let's look at tables P, Q, and R, just so we can be familiar with them. Here's table P. It tells us the prefix that we shall use for the number of carbons that we have. It's important to know that these prefixes are used for the number of carbons in the longest continuous chain in a compound. We'll talk more about that in a minute. Here's table Q, which talks about hydrocarbons. Obviously, these are compounds that are made only of hydrogen and carbon. As you can see here, hydrocarbons, hydrogen and carbon only, hydrogen and carbon only. Homologous series. A homologous series of hydrocarbons would follow either this general formula, or this general formula, or that general formula. This general formula is for the compounds, for the alkanes, which names will end in A-N-E. This is for the alkenes, which names end in E-N-E, and this is for the alkynes, which names end in Y-N-E. And here's table R, which contain a bunch of different classes of compounds: halides, alcohols, ethers, aldehydes, ketones, organic acids. And similarly, they have to have a specific ending. If it's an organic acid, the name would always end in anoic acid. A ketone will end in anone. Aldehyde will end in anal. Ether will end in ether. Alcohol ends in anol, and so on. Propanamine ends in anamine. Anamide. Functional groups, very important. We talked about those functional groups when we talked about isomers in the beginning. I believe that was the first video. What isomers are, they have the same chemical formulas, but they have different functional groups, and because they have different functional groups, they have different structures, and because of that, they have different properties, different physical properties, different chemical properties. Okay, so now that we're familiar with those three tables, let's read a little bit. Let's perform a little a short reading exercise. This should say table P, not table R. This table Q is only used if we have a hydrocarbon compound. So saturated hydrocarbons, all the carbons must be single bonded. They're classified as alkanes. So alkanes are single bonded carbons. Single bonded saturated. It actually goes as single bonded saturated substitution. We'll talk about substitution when we get to the types of organic reactions. Because go on, alkanes and their names end in A and E. Example, propane is an example of a saturated hydrocarbon. It ends in A and E. It belongs to the alkane group, made of 3 carbons, and all those carbons are single bonded. In an unsaturated hydrocarbon, there's at least 1 double bond. All you need is 1 double bond or 1 triple bond between 2 carbons. Any of the 2 carbons in a carbon chain, if they're double bonded or triple bonded, you have an unsaturated hydrocarbon. These are, if it's a double bond, it's classified as an alkene. If it's a triple bond, it's classified as an alkyne. YNE. 2-pentene represents 5 carbon chain that contains a double bond located after the second carbon. So let's analyze this a little further. 2-pentene. The numbers are always locations of whatever is attached to the functional group. So of whatever is attached to the carbon chain. So the numbers that you're seeing are always locations of whatever you have that's attached to the carbon chain. So what's the carbon chain? Here's the prefix for it, pent. We can go to table P to identify what this means. If we have a pent, we have a 5 carbon chain. Okay? So pent means 5 carbon chain. So here are 5 carbons. 1, 2, 3, 4, 5. We had 2-pentene. Just as a reminder, we had 2-pentene. Pent is 5 carbons. We got this out of the way. Now we have a 2-ene, which means on the second carbon, location, on the second carbon, there's an ene, E-N-E. What does E-N-E mean? Going here, we see E-N-E means we're talking about an alkene, and an alkene has double bonded carbons. E-N-E means we have a double bonded carbon. So we have 2 on the second carbon. Here's the first carbon, this carbon number 1. On the second carbon, we have a double bond. Okay? Now everything else will just connect normally. So this carbon will connect with this carbon, single bond, single bond, single bond. And now we know that carbons have 4 valence electrons according to the periodic table. We can go back here and check. Carbon has 4 valence electrons, which means that carbon will bond 4 times. Each carbon will bond 4 times. So let's take a look here. Going back to my drawing, this is called a structural formula. I'm drawing a structural formula. So this carbon is bonded 1 time already with this carbon. And now this carbon would have to bond, sorry about that. There we go. This carbon would have to bond 3 more times. And since we're talking about a hydrocarbon, there is no functional group attached to it. It's only hydrogen and carbon. Obviously, it will be bonding to hydrogens. This carbon here is already bonded 3 times. 1, 2, 3. Therefore, it doesn't need 4 hydrogens. It only needs 1 hydrogen. This one's the same way. It's bonded 1, 2, and 3. It only needs 1 more hydrogen. Now, it doesn't matter whether you put that hydrogen here or you put it here. It doesn't matter. At least for the purpose of general chemistry. When you get to college, you will know cis and transformations, and it actually makes a difference. Now here, this carbon here is bonded once, twice, so it needs 2 more hydrogens. And this carbon here is bonded once, so it needs 3 more hydrogens. Now, if I was actually to write the chemical formula for this, or the molecular formula, it would be C, 1, 2, 3, 4, 5 carbons. H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. And this actually corresponds with the alkene formula, right here, the alkene general formula, which says that C the number of carbons, N for the number of carbons, C the number of carbons, H double the number of carbons will always reference an alkene. So in that case, we have C, 5, the number of carbons is 5, H was double the 5 to give me 10. So this is an alkene. Now, if I was to actually predict what the next alkene in this homologous series is going to be, it is going to be C6, because after 5 carbons, I'm going to have 6 carbons. H, double the carbons, I'm going to have 12. And this would be called 6 carbons. The prefix is hex. And since it follows the alkene formula, this will be hex ENE. Next one would be hept ENE, and it would have the formula C7, H, double the 7, 14. Next one would be oct ENE, and it would have the formula next one would, C8, H16, then nonene, C9, H18, and so on. Okay. So, if I was talking about an alkyne, let's say I have ethyne. Ethyne would be eth stands for 2 carbons, 1 carbon, another carbon, and then YNE means that we have a triple bond between the carbons. Here's the example. So these carbons would be triple bonded, and since each carbon bonds 4 times, this carbon is bonded 3, so it would need 1 more hydrogen, and this carbon is bonded 3 times as well, 1, 2, 3, it needs 1 more hydrogen. Okay, the next organic compound in this alkyne homologous series would have 3 carbons, so it would be C3H. Notice the formula here. Now my formula is H double the carbons, double the N, double the number of the carbons, minus 2. So H double the 3, that's 6, minus 2, that's 4. So C3H4 will be the next one in this homologous series, the next alkyne in this homologous series, and it will be called, for 3 carbons going here, it would be prop, and the ending obviously will be the same, prop YNE. Okay, and if I was to draw this, I could draw it like this: 1, 2, 3 carbons, and I would have a triple bond here between any of those 2 carbons, and then I would have single bond here, and then I would have a total of 4 hydrogens. So 1, 2, 3 bonded, this carbon is bonded 3 times, it would need 1 more hydrogen. This bonded is already bonded 4 times, 1, 2, 3, 4, so it doesn't need any more hydrogens. This carbon is bonded only once, so it needs 3 more hydrogens, 1, 2, 3. And now I have a total of 1, 2, 3, 4 hydrogens, which obeys my my formula, my organic compound formula here, and then I have 3 carbons, which obeys my organic compound formula as well. Okay. Now, just one more example. If I said I want 2 pentyne, then I would have 1, 2, 3, 4, 5 carbons, and then there would be a triple bond here. And then everything else will be single bonded, and I will add my hydrogens as well. This one does not need a hydrogen because it's already bonded 4 times, so I just need 1 hydrogen here. Sometimes I may ask you for, let's say, 2, 3 pentadiene. What does this mean? This means that I have a pent chain, 1, 2, 3, 4, 5, and I have 2 diene. Diene means 2 double bonds. two double bonds. Di for two, ene for double bond. Where are they located? One double bond would be on the second carbon, the other double bond would be on the third carbon. So here I'm going to have a double bond here, on the second carbon, so this is carbon 1. It helps to actually number those carbons. So this is carbon 1, this is carbon 2, so on the second carbon I have a double bond, and on the third carbon I have a double bond. All the other carbons will be single bonded. Okay. So now just add the hydrogens. So here I'll have 1, 2, 3 hydrogens. This one needs one more. This one needs nothing. This one needs one more. This one needs 3 more. Okay, get rid of those numbers at the end. All right, so that's how you draw 2, 3 pentadiene. Remember, in 2, 3 pentadiene, the double bond will come after the second carbon, not before the second. This is carbon 1, this is carbon 2. So the double bond will come after the second carbon. Okay? Put that hydrogen back. And then after the third carbon. All right, so that's pretty much it for table P and table Q. Let's go back to our readings, and you may be asked the question, which of the following represents a saturated hydrocarbon? So you may be asked the question like, is it A, C3H8, or is it B, C3H6? Now saturated, remember, saturated single bonded substitution. Saturated compound, a saturated hydrocarbon would have only single bonds between the carbons, and therefore must be an alkane and must follow this formula. So choice A here follows that formula. C3, the number of carbons is 3. H2 times 3 is 6, plus 2 is 8. So this is your answer. This is a saturated hydrocarbon. Sometimes you may be asked a question that's a little more confusing. You may be given something like this. Which one of those is unsaturated? You'll get 1, 2, 3, 4. So you'll have this, and then you'll have this. So if you're given a question whether it's A or B, and you're asked which of the following is an unsaturated hydrocarbon, the answer is choice A. Why is it choice A? Because we're talking about an unsaturated hydrocarbon. So here's your hydrocarbon, hydrogen and carbon only. This one contains oxygen. Okay. Now, let's go back to our readings. Here we go. When you're given a structural formula, find the longest continuous chain of carbons. And let's just be clear about what that means. The chain of carbons doesn't have to be just straight to be continuous. This chain is made of 5 carbons. It's straight this way, but I can make that same exact continuous chain this way. 1, 2, 3, 4, 5. It's still a continuous chain. How do I identify a continuous chain? I will grab my pen, and I'll see if I can draw a straight line through the chain without raising through all the carbons, without raising my hand off the paper, or without raising my pen off the paper, okay, and without having to go backwards. So let's see, can I do this? I start from here, I'm going through every single carbon without having to go backwards and without raising my pen off the paper. Okay, sometimes you may not have you may have an attachment to the continuous chain. So let's say, for example, you have something like this. The same chain of 5 carbons, so 1, 2, 3, let's say 4 carbons now, and then you have something like this here. So here, the longest continuous chain actually contains 4 carbons, not 5. This carbon is an extension. So here I have 1, 2, 3, 4 carbons, and this carbon is an extension. When you have a carbon extension, we usually give it the YL ending. So if you have a single carbon extension, we call it a methyl. Meth for one carbon, YL, because it means it's an extension to that carbon chain. So methyl, this is a methyl group. If I had something like this, 1, 2, 3, 4, and then here I had 1, 1, 2. So here, my longest continuous chain is still 4 carbons. 1, 2, 3, 4. Or you can actually consider it like this. 1, 2, 3, 4. That's still the longest continuous chain. But no matter how you look at it, on the second carbon, so this is carbon 1, this is carbon 2, on the second carbon, you will have 2 carbons attached to that chain. So if you're looking at the green chain, these 2 carbons will be attached to the second carbon. If you're looking at the red chain, these 2 carbons will be attached to that red chain. Okay, so these would be, so in this case, the name of this would be 2F for 2 carbons, YL to indicate that they're attached to the chain, and then the chain name, since it's all single bonded, is bute. The longest chain has 4 carbons, so the prefix for 4 carbons is bute, and all these carbons are single bonded, so ANE is the ending. I know that was a little difficult, so let's review it again. Whatever is attached to the chain, you got on the second carbon, you have an ethyl group. The name of the chain is bute, has a prefix of bute, because 4 carbons is what's present in the chain, and then you have an ANE ending, because all the carbons are single bonded. It helps to actually just write down the name of the chain first, the name of the longest chain first, so you'll start with butane, and then you will write down whatever is attached to it. Okay? Sometimes you may have something else attached to it, maybe a halogen from group 17. So let's say, for example, you have that same 4 carbon chain. Maybe you have something like this, Br and Br. So what would this be? The name of the chain is bute, again, and has an ANE ending because all the carbons are single bonded. And then you have a bromine and another bromine attached here. A bromine on the second carbon and a bromine on the third carbon. So this would be 2, 3. On the second carbon I have a bromine. On the third carbon I have a bromine. Di, because I have 2 of them, bromo. 2,3-dibromo-butane. Why did I make the ending O? Why didn't I just say dibromine? Table R tells you why. Take a look at table R. Here's table R. If you have a halogen, a halide, halocarbon functional group, the ending will be O. Fluoro, chloro, bromo, iodo. Okay? Now, what if I have something like this? What if I have something like this? 1, 2, 3, 4. And I have a bromine here. What would the name of this be? Would it be 1, 2, 3, 4 bromo? Or would it be 1 bromo? The answer to that question is, it would be 1 bromo. Because we have a rule, and the rule says you always number the carbons in a chain starting from the end that's closest to the functional group or closest to the double bond or triple bond. So this is considered a functional group, an attachment to the chain, or something that does not usually come on a chain, on a carbon chain. So we number the carbons starting from the end that's closest to the functional group. So this here would be carbon number 1, and this would be carbon 2, carbon 3, carbon 4. So when I name this, I would call this butane as well. Butane, ANE ending, because all the carbons are single bonded. But now the name of this would be 1-bromo-butane. Again, you start numbering the carbons from the end that's closest to the functional group. What if there was like a functional group and a double bond? Then you would say the name of this would be something like this: 1-bromo. Okay, on the first carbon there is a bromo, and on the second carbon there is an E-N-E ending to the chain, but. Okay, so first carbon there is a bromo, second carbon, right after the second carbon there's a double bond, and which makes the name of the chain ene, butene. And that double bond is on the second carbon, hence why I have 2-butene. Okay? Now, we talked about halogens, we talked about double bonds and triple bonds, and now we're going to talk about table R stuff. Okay? So here's how let's read a little bit here, because this talks a lot about table R. Okay. But. Always start from the end that's closest to the functional group or double or triple bond. Functional group takes precedency over double or triple bond. That pretty much explains what I just said. Methyl, YL, for hydrocarbon functional groups. Alcohols will have an anol, aldehydes will have an anal, ketones anone, organic acids anoic acids. So let's take a look at table R stuff. Here are table R stuff. Very important that you're able to identify the functional groups. Okay? Identify the classes of compounds and identify the endings. If you know the ending, according to table R, you know the name. So, if you see an OH attached to a carbon, know that the name of that chain must end in anol. If you see an O trapped between two carbons, know that the name of that chain must end in the word ether. And the left chain and the right chain will have a YL extension. If you have a carbon, the R stands for the letter carbon, attached to another carbon, which is attached to a double bonded O and an H, we're going to end in anal. A carbon chain attached to another carbon, which is double bonded to an O and then attached to another carbon from the right side, then we have an anone. If we have a carbon chain attached to a carbon that's double bonded to an O, and then attached to an OH group, we have an organic acid, and we call it, and when the ending of the chain would be anoic acid. Esters. Carbon attached to another carbon, which is double bonded to an O and attached to another O, which is attached to a carbon chain. This would be YL and then anoate. So this carbon chain here, the carbon chain that's here, will end in YL, and the carbon chain that's here, including this carbon, will end in anoate. Esters are a little weird. So if this was methyl propanoate, methyl propanoate. So this here would be your propanoate, and that there would be your methyl. Okay, amines, anamine, single nitrogen, attached to carbons from many different directions. Anamide is when there is a carbon that's double bonded to an O and attached to a nitrogen and a hydrogen. Okay. Now, let's give some examples of these so you have a better understanding. Okay. Propanol. Prop, according to table P, is 3 carbons. Anol, one of those carbons, the first one, has an OH ending. So here are my 3 carbons, and this first carbon has an OH. And then the rest will have just a bunch of H's. Each carbon has to bond 4 times. Always double check how many times your carbons are bonded. Now if I drew this like this, with an OH here, that's still fine. This is still 1 propanol. And this is 1 propanol. Why? Because remember, we count from the side that's closest to the functional group. So in this case, I'm starting from the right. Sorry. And in this case, I'm starting from the left. Okay. So that's 1 propanol. Let's try another one. Methyl ethyl ether. So here I have an ether, which is simply just an O. And on one side of the ether, I'm going to have a methyl, which is a single carbon. And on the other side, I'm going to have an ethyl, which are 2 carbons. Meth is the prefix for 1 carbon. Eth is the prefix for 2 carbons. Okay, now just make sure you add the hydrogens. Each carbon must bond 4 times. This carbon's already bonded once. 2, 3, 4. This carbon's bonded twice. So 3, 4. This carbon is bonded once. 2, 3, 4. That's methyl ethyl ether. Propanol. 1, 2, 3 for 3 carbons. Prop, 3 carbons. And I have an anal, which is a double bonded O. That's really all that it is, and an H. So, in this case, I cannot call this a propanol, because that carbon that has the double bonded O must also be attached to an H. So this doesn't work. This may work. A double bonded O and an... One second. A double bonded O and an H. This may work. Or 1, 2, 3. This may work. This is propanol. Add the hydrogens. Okay. Now, next one. 2 pentanone. This means that on the second carbon, I'm going to have an anone. And an anone means a double bonded O. That's it. Okay, so pent stands for 5 carbons. 2, 3, 4, 5. And on the second carbon, I have an oxygen. Now just add the hydrogens. This carbon does not need any more hydrogens. These do. And you're all set. Next, propanoic acid. Prop, 3 carbons. Anoic acid means that one of those carbons is attached to an O and an OH. So, here's the carbon attached to an O and an OH. Here I have a propanoic acid. Okay. Next, methyl propanoate. So, anoate means that you have a double bonded oxygen and another oxygen. And this is attached to one functional group here. And this is attached to another functional group here. So methyl propanoate. So here's the name, methyl propanoate. So the propanoate is going to have to be on that side. I already have 1 carbon here attached to the anoate. And now I'm going to have just 2 more carbons here to give me the prop. 1, 2, 3, anoate. And now the methyl is just going to be right here. 1 carbon with 3 H's. Make sure you add the H's. Propanamine, same way. Propanamide, same way. So that's pretty much how to write the structural formulas of organic compounds. Let's just go back to the readings, make sure that we did not miss anything. Just more examples, more examples. Oh, sometimes you'll have something like this. And what you should know is that this is usually just a structure that's drawn to abbreviate, to draw less carbons so that we don't make it too messy. So this actually means that there's a carbon right here attached to the chlorine. There's a carbon right here. On every corner there's going to be a carbon. There's one right here. This one is already here present. They drew this one. They drew this one. There's one right here. They did not draw anything here, so there's one right here. Okay. And that's pretty much it. That's everything you need to know about organic chemistry, naming and writing. Let's go back to the questions, see if you know how to answer them. Determine whether the following statements are true or false. All right, everybody, thank you very much.